This video is about angles of a polygon, and it's found in your text in section 3-5. A polygon is a figure formed by line segments such that each segment intersects exactly two other segments, one at each endpoint. So we can all think of some examples of polygons, many-sided figures. They could have lots of sides. They could even be shaped something like this. This is called a concave polygon, excuse me. But all of those are polygons. Some non-examples of a polygon would be a shape that is enclosed but contains a curved part. So that's not a line segment, therefore this can't be a polygon. Another non-example could be something like this. Yes, it's made out of line segments. Yes, each line segment intersects two other line segments, but they don't intersect the other line segments at each endpoint. So that's where the definition breaks down for this figure. Another non-example of a polygon could look something like this. This segment here is intersecting two other segments at its endpoints, but it's also intersecting a third segment here. So that keeps this figure from being a polygon. Now, a convex polygon means that no line containing a side of the polygon contains a point in the interior of the polygon. I think it's easier to understand this definition by looking at some examples and non-examples. Some examples of convex polygons are these. Some non-examples of convex polygons. One is like one of the figures that I showed you in the last slide. In this figure, suppose we extended the line containing this segment. Now, the line containing a side of the polygon contains a point in the interior of the polygon. All of these points in the interior of the polygon are part of this line, and for a convex polygon, no line containing a side of the polygon can have points inside. So that disallows this from being a polygon. A convex polygon. A regular polygon is a polygon that is both equilateral and equiangular. A square is an example. All the angles in a square are congruent, and all the sides of the square are congruent. Now this shape over here also has congruent sides, but what keeps it from being a regular polygon is that this angle is clearly not congruent to this angle. So right there, we have equiangular is not true of this shape. Here we have another regular polygon. All of its angles are congruent, and all of its sides are congruent. I guess I should be double marking all of these things so that we don't start thinking this aligns with the other diagram. But the non-example corresponding to this would be this figure, which does still have its angles all congruent to each other. But clearly its sides are not all congruent. This side is not congruent to this side, for example. So this makes this not a regular polygon. Naming polygons. To name a polygon, we simply list the vertices in consecutive order. So examples of how we could name this polygon would just be, we could call it a quad. Usually a four-sided figure is a quadrilateral, so we sometimes abbreviate that quad. A, B, C, D. We could also start from a different vertex and call it quad DCBA, because that still goes around the figure in consecutive order. Ways that we could not name this polygon would be quad BACD, because there we're going BA over to here and back to there, and we can't do that when we're naming a polygon. Okay, here's your first theorem about polygons, and polygons' interior angles are the angles inside of each vertex. And the theorem simply says that the sum of the measures of the angles of a convex polygon with n sides is equal to this expression here, n minus 2 times 180. So just to do a quick example, this figure here is a pentagon because we have 5 sides. So for this figure, 5 equals n. Now we can plug that into this expression here. So we have n minus 2 times 180, which gives us 5 minus 2 times 180. So 3 times 180 gives us 540 degrees. So what we're finding here is that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, all of these angles added up will equal 540 degrees. Now you try one. What's the interior angle sum for an octagon, a figure with 8 sides? Okay, here's another definition for you. A diagonal of a polygon is a segment joining two non-consecutive vertices. So let's remind ourselves what vertices are. These are vertices. And non-consecutive means they don't come right after each other. So, for example, this segment is a diagonal of this figure here. And we could also draw a diagonal like this. But drawing a segment from this vertex to this vertex is not a diagonal. It's actually one of the sides. So it's pretty clear that it's not a diagonal. Let's draw some more diagonals here. On this figure, I'm going to draw all the diagonals that start from this particular vertex. And I'm going to do the same thing on this 5-sided figure. And notice that these diagonals are kind of wiggly here, but are dividing up this entire polygon into a number of different triangles. And this observation can actually help you prove the polygon interior angles theorem by noticing how many triangles are created by all of the diagonals that start at one vertex. Let's do another example. A baseball diamond's home plate, which is a 5-sided figure, has 3 right angles. Let's mark them here. 1, 2, 3. The other 2 angles are congruent. Okay, so we have these 2 angles congruent. Find their measure. So let's call each of these angles x. Since we know they're congruent, they have the same measure. And using the interior angles theorem, we've already found out that for a 5-sided figure, we know that the total interior angle measure was 540. We calculated that in the last example. So what we have here is 5 interior angles. We have 3 90-degree angles. So I'm going to say 3 times 90 degrees plus, now we have 2 of these mystery angles, 2x. must total 540 degrees because this is a five-sided figure. So now we can do some algebra. 3 times 90 degrees is 270, plus 2x equals 540. Subtracting 270 from both sides, 2x equals 270. X equals 135 degrees. And I actually made this diagram, so it's believable that x could be about 135 degrees. You try one. Four of the angles of a pentagon have measures 40, 80, 115, and 165. Find a measure of the fifth angle.
My fellow citizens, I know that this is a competitive speech, but I've been eating eyelashes and it's great. It helps me focus and it's amazing. Here's some words from the maker Raleigh. Oops, wrong person. There. Hi. What caused you to make this great thing? Well, I broke my finger bad, and I needed to eat healthy. I wanted candy, so I made this healthy candy called Alice's. So good. Thanks for your time. Have a nice day.
Let's move on to the polygon exterior angles theorem. Remember that just as in triangles, we have exterior angles formed by extending one of the sides of the figure further out, and then we have this angle that's formed outside of the figure. The sum of the measures of the exterior angles of any convex polygon, no matter how many sides the polygon has, is always 360. This is a very surprising theorem because it seems like it should matter how many sides the polygon has, but it turns out it doesn't. So for this figure here, we have measure of angle 1 plus measure of angle 2 plus measure of angle 3 plus measure of angle 4 plus measure of angle 5 must equal 360 according to this theorem. Now the polygon exterior angles theorem can be proved algebraically from the polygon interior angles theorem. So maybe I'll challenge some of you to try that. But the in-class investigation that we'll be doing should also help convince you that this theorem is true. For further practice, see page 104, numbers 3, 5, 11, 13, and 15.